So in this one, we're going to identify the strongest type of intermolecular force. Again, we're always more interested in the strongest type. So a few things with this. Remember, ionic is greater than hydrogen bonding, greater than dipole-dipole, greater than London dispersion forces. London dispersion forces, these are for nonpolar. That's the strongest type for a nonpolar molecule. For polar, you can have hydrogen bond or dipole-dipole. Again, we have to decide when we look at that molecule, and then ionic, of course, is just for an ionic compound. First one, so this is argon. So again, this is a noble gas. So these things by themselves, this is a nonpolar molecule, and so London dispersion forces. That's the only type that it can have. And again, remember, just one last time, all molecules can have London dispersion force or do have London dispersion forces, but we're always interested in the strongest type with that. HCl. So in this case, this is again, I go by electronegativity. This is a polar molecule, but it doesn't have hydrogen bonding. The hydrogen bond is very specific. Oxygen and hydrogen, nitrogen, or fluorine, none of these is in there. So even though this is a polar molecule, it has hydrogen, it's not hydrogen bonded. So in this case, this would be a dipole. Third type, HF, hydrogen fluoride. This one's actually hydrogen bonded, right? It has hydrogen and fluoride in there. So this is H bonded. This other one, calcium chloride, identified as ionic compound. So this is ionic. So basically, remember, calcium has positive 2 charge. Each chlorine is -1, etc. If it's an ionic compound, it's going to have ionic forces with it. So to kind of finish this off, for some of these we have to draw out the Lewis structure to determine if it's a polar or non-polar molecule. So this is CH4, this is methane. If I draw it out, the carbon-hydrogen bonds are non-polar, and this is a non-polar molecule overall. So the strongest forces are going to be LDF. Again, if it's a non-polar molecule, it only has LDF forces. We write those down. Carbon monoxide, I drew out the Lewis structure with it. You have a partial negative on oxygen, partial positive on carbon. So this is a polar molecule. Doesn't have hydrogen bonded, so it's going to be dipole-dipole. Let's just say dipole. So again, identified as polar or non-polar to begin with. NaNO3, ionic. Whenever you have a metal, it's ionic, so it's going to be ionic forces. That's simple enough. Let's look at carbon dioxide. This is always kind of a classic one. If you look at the Lewis structure, so even though the carbon-oxygen bond is polar, remember, if a molecule is going to be polar overall, it's a vector. It depends on magnitude and direction. They're on opposite ends. They'll cancel each other out. So this is a non-polar molecule. So it's one of those cases, polar bonds, non-polar molecule. Non-polar molecule is going to be LDF. One more thing with this. Say I changed this one right here. So I have methane. Say I changed it. Say I put a chlorine up there. So in this case right here, I've changed this to a polar molecule. Polar. And then it'll be dipole. One last thing, since I got this molecule up here, if all 4 of these were chlorine, and this is something we did when we did Lewis structures, but it's always good to review. So in this case right here, even though the bond is polar, everything cancels out. So if you have a tetrahedral structure, all 4 of them are the same. It all cancels out. So this is a nonpolar molecule. So nonpolar, and then LDF, the London dispersion